All right, so in the last video, we were working through our first example, trying to figure out what the upper bound on our remainder term would be for that second degree Taylor polynomial that we worked out. I needed to punch it into a calculator, so I did that, and then I ended up getting this value right here. This is approximately 0.000974. So the fact that I have 3 zeros after that decimal point indicates that if I use this second degree approximation for that function x equals negative or x to the negative 1/2 for any number x that I could plug in from this interval, then I will be at most or I'll have basically 3 decimal places of accuracy in my answer. Let's do one more example just to get something else under our belts. Approximate f of x equals x times the natural log of x with a third degree Taylor polynomial centered at 1. Estimate the accuracy of the approximation on the interval 0.5 to 1.5. It's tempting to look at that and think, oh wait, I know a Taylor series for the natural log. Let me try and use that. Remember that Taylor series that we came up with previously is for the natural log of 1 plus x, not the natural log of x. And there's not as straightforward of a substitution that helps as much as you might expect it to here. This is an easy Taylor series to come up with, though, just by hand. So, for example, we have f of x equals x times the natural log of x. What is f prime? Well, of course, I'm going to need the product rule here. So derivative of x is 1 times the natural log of x plus x times the derivative of the natural log, but x times 1 over x is just this. So I get the natural log of x plus 1. And then the rest of these are pretty straightforward. We need up to the third derivative for my Taylor polynomial, since it's a third degree Taylor polynomial. This is going to equal what? This is equal to just 1 over x. F triple prime then is going to equal negative 1 over x squared. We're centering our Taylor polynomial at 1, so I need to plug a 1 into each one of these. F of 1 is 1 times the natural log of 1, which is 0. F prime of 1 is the natural log of 1 plus 1, that's 1. F double prime of 1 is 1 over 1, which is 1. And then negative 1 over 1 squared, which is f triple prime of 1, that would be negative 1. So I'm getting really nice coefficients here. Okay, finding my Taylor polynomial, that's the next step. So the Taylor polynomial T3 of x is going to equal my constant term, which is 0, don't even need to write that, plus 1 times x minus 1, so I'll just write x minus 1 there, plus 1 over 2 factorial times x minus 1 squared, plus negative 1, so let's actually write that as a minus, 1 over 3 factorial, x minus 1 cubed. I can write this as x minus 1 plus 1/2 x minus 1 minus 1/6. 3 factorial is 1/6 x minus 1 cubed. So there's my third degree Taylor polynomial. And now what I'm going to need is that upper bound. So I'm going to apply Taylor's inequality. R3 of x, I'm going to take its absolute value that's less than or equal to what? Well, I need to find that number m that we talked about before. So what is m? Again, m comes from the n plus 1th derivative. In this case, the n plus 1th derivative is going to be the 4th derivative of x, or of f of x. So taking the derivative of this guy right here, I'm going to get 2 over x cubed, okay? And we want to bound this on this interval here. Well, once again, because I have an x in my denominator, the largest I can make this is by using the smallest available value for x. This lower bound here is 0.5. So this is going to be less than 2 over 0.5 cubed. Okay, 2 over 0.5 cubed. So 0.5 is the same thing as 1/2. 1/2 cubed is 1/8. 2 divided by 1/8 is the same thing as 2 times 8, so that's 16 right there. Okay? Now, what do we need to do next? I need to take that 16 right there and use that as the m, so I'm going to say equals m in this expression up here. So we're going to have 16 over n plus 1 factorial. Remember, n was 3 in this example, so n plus 1 is 4. I have 4 factorial there. And then we also need to multiply that, so let me go back to my previous page here, by, here it is. Nope, that's the wrong one. Where is, oh, here it is. We need to multiply that by the absolute value of x minus a to the n plus 1 power. Remember, x minus a is that radius of this interval right here. Like the previous example, it's 0.5 again. Okay, so coming up here, 0.5, or I could even write it as 1/2, and this time, again, it's to the 4th power. Okay, now let's look at this for a moment. 4 factorial is 24, and 1/2 to the 4th power is 1/16. So I'm going to have 16 here, and I'm going to have 1/16 here. Those are going to cancel, and I'm left with 1/24. So this is an upper bound on my remainder term. It's not as good of an upper bound as the previous problem. So for this particular function, if I want better accuracy, I need a higher degree Taylor polynomial. But that's essentially it. That's all we're doing in this section. So you should be good to do the homework. You're looking at approximating functions with Taylor polynomials and then bounding those remainder terms to determine how good of an approximation that you have.